Hello everyone, I am Manthan Patel and I will be presenting our studio work on in-situ slum redevelopment project situated in Ahmedabad. The studio focused on understanding real-time construction execution, monitoring, planning, coordination, quality control and project management practices adopted in a large-scale residential redevelopment project. This is an in-situ slum redevelopment project developed under the PPP model on a turnkey basis and follows the PMAY Urban Slum Rehabilitation Policy 2013. The project is a brownfield redevelopment aimed at rehabilitating existing slum dwellers on the same site. The project started on 1st June 2023 with the proposed completion in March 2027 and has an approximate project cost of 150 crores. The scope follows the design, build, finance, operate, maintain, transfer approach. The development consists of 19 residential towers of G+7 floors planned in 4 phases, providing a total of 2,170 dwelling units and 36 shops over a plot area of approximately 31,678 square meters. The project also includes transit accommodation supports and Corpus Fund provisions for beneficiary welfare and long-term maintenance. The main objective of the project is to provide safe and dignified housing, improve land utilization, and redevelop the area with better infrastructure and planned urban development. The project further formed the basis for our studies in equipment planning, quality management, and material management discussed in the following slides. In today's construction industry, construction equipments are a vital resource. They account for 15 to 40% of the total project cost. The study included earth moving equipments, lifting equipments, reinforcement yard equipments, and RMC equipments, including batching operations. The selection of equipment was based on productivity requirements, execution duration, operational efficiency, and cost optimization. In the site layout, we can see different equipments are deployed on site. The RMC batching plant with aggregate storage is located at the entry. To the left is the pile rigger and backhoe loader. After that, the material lift, reinforcement yard with on-site QA/QC lab facilities are also shown. The equipment movement are indicated with black dotted lines. In the right, the list of earth moving equipments required for excavation, hauling, backfilling and compaction activities are shown. In our site, there were some blocks in which raft foundation was done and some blocks had pile foundation. One of the equipment used for excavation is Komatsu PC210. It has a daily productivity of 624 meter cube, which is about 78 meter cube per hour. The quantity to be excavated for one block is about 20,309 meter cube, and the duration considered is 14 days, which gives roughly about 495 meter cube of excavation per day. So the production required is less than the productivity, meaning the number of excavator to be deployed is 1. Similarly, the deployment requirement for other equipment was calculated. For the lifting operations on site, there were no such specific equipments. So we are proposing a mobile tower crane. A Spring SK126586 mobile tower was proposed. A cost comparison was performed between rental and ownership models. The total hiring cost for 63 months was calculated as approximately 49.30 lakh rupees. On the other hand, the ownership cost for the same duration was about 157.40 lakh rupees. This means the ownership option was nearly 3.2 times more expensive than hiring. Moving forward to the reinforcement equipments. The reinforcement yard planning included bar cutting machines and bar bending machines. The total steel yard area planned was approximately 139.89 square meters. Operating cost included electricity charges, labor cost, and steel foreman cost. The operating cost per machine per day was calculated as approximately 4,026 rupees. The total reinforcement equipment cost at peak operation was about 21,39,427. At peak stage, the total reinforcement quantity handled was around 2,92,882 kgs. This resulted in an equipment handling cost of approximately 7.3 rupees per kg of reinforcement. The project proposed a 50 cubic meter per hour capacity of RMC batching plant. The equipment setup included cement silos, transit mixers, concrete pumps, and needle vibrators. The total RMC equipment cost was calculated as approximately 1.52 crore rupees. The total plant concrete quantity was approximately 51,740.92 cubic meters. Based on these, the equipment cost per cubic meter of concrete was about 293.62 rupees. The study also evaluated machine depreciation, maintenance insurance, and salvage values. These helped us understand life cycle costing of construction equipments. The next important area studied was the quality management plan, which included the quality assurance plan as one of its key components. The QAP covered major aspects such as quality objectives, document control, procurement procedures, inspection and testing plans, method statements, NCR management, audits, and handover procedures. The project follows a structured quality management system involving the client, developer, contractor, PMC, and third-party testing agencies. According to the tender clauses, the contractor is required to maintain a fully equipped on-site quality control laboratory. Approximately 70% of testing is conducted at the site laboratory, while 30% is carried out at external laboratories, in which 15% in government laboratories and other 15% in private laboratories. Concrete quality verification is done as per IS 456 standards. The contractor is also responsible for all testing and quality control expenses. The project uses a fully automatic computerized batching plant for design mixed concrete. The project management consultancies plays a major role in project execution and monitoring. The PMC is mainly responsible for project planning and monitoring, quality supervision, stakeholder coordination, billing verification, and reporting. The PMC acts as an interface between the client, contractor, and developer to ensure a smooth execution. The organization structure shows a clear hierarchical communication and reporting systems among all project stakeholders, which helps maintain effective coordination, accountability, and quality control during project execution. The client side mainly performs administrative supervision and approval functions. The developer is primarily responsible for planning, management, and execution control, while the contractor handles on-site construction activities through engineering and QA/QC teams. A detailed study of quality control documentation was carried out. This included checklists, inspection reports, method statements, and non-conforming reports. The NCR system helps identify defects, analyze root causes, and implement corrective actions. The QA/QC team from contractor side prepares and maintains NCR records, while the PMC reviews and approves them. A checklist is prepared to ensure work is completed systematically, accurately, and according to the required standards and safety procedures. The RCC checklist includes pre-pour inspections, slum test, cube testing, reinforcement checks, safety checks, and post-pour inspections. The study also highlighted the importance of documentation and record management in maintaining construction quality. The quality management plan also included linear responsibility charts and RACI matrices to understand stakeholder involvement. A RACI matrix was prepared where R stands for responsible, the person who performs the activity. A stands for accountable, the performs ultimately answerable for the activity. C stands for consulted, stakeholders whose inputs are required. I stands for informed, in which stakeholders who are updated about progress. Two types of analysis were carried out from the matrix. First was the vertical analysis. Vertical analysis studies the involvement of each stakeholder across all project activities. In this analysis, we counted how many times each stakeholder was marked as responsible, accountable, consulted, or informed. This helped identify which stakeholder had the highest participation and decision-making authority during execution. From the analysis, we observed that the developer had the highest involvement during construction execution. The client's role was mainly focused on consultation and periodic review, while the PMC was mainly responsible and accountable for maintaining quality in construction stage. This analysis helped us understand accountability, communication flow, and decision-making hierarchy on each level within a large project. The second analysis done was the horizontal analysis. In the horizontal analysis, each activity is analyzed individually to understand how responsibilities are distributed among different stakeholders involved in the project. This analysis helped identify whether an activity has a balanced responsibility structure or whether there is an excessive dependency on certain stakeholders. It also helps evaluate coordination requirements, communication complexity, and decision-making efficiency for each construction activity. For every activity, the number of people marked as responsible, accountable, consulted, and informed is counted and interpreted. Activities having multiple responsible persons indicated shared execution responsibilities. While this improves collaborative working, it may sometimes create confusion regarding ownership of the task if roles are not clearly defined. Overall, the horizontal analysis showed that activities with balanced responsibilities and accountability structures perform more efficiently, while activities involving excessive consultations or too many responsible persons may face coordination challenges and slower decision making. Therefore, proper role clarity and controlled stakeholder involvement are essential for effective project execution and quality management. Next, moving forward to the material and inventory management. Material management plays important role as it helps in controlling materials and reducing overall project cost. In most construction projects, materials like cement, steel, aggregates usually make up for 50 to 60% of total share. A detailed material inventory management study was carried out using the classic EOQ models along with lead time and material inward flow analysis. The material inward process shows the systematic flow of AAC block procurement, starting from estimating the requirement and supplier coordination to transportation, material receipt, and recording at site. This helps maintain proper inventory control and uninterrupted workflow. The transportation analysis shows the total delivery cycle takes approximately 8 hours, including loading, unloading, and travel time. The lead time study includes purchase requisite generation, approvals, PO processings, testings, and GRN issuance, resulting in a total lead time of around 6 days. This highlights the importance of advanced procurement planning. Using the classic EOQ model, the optimum order quantity for AAC blocks was found to be approximately 377.37 cubic meter, where ordering cost and carrying cost are balanced at around 35,850 rupees, resulting in a minimum total inventory cost. The graph shows that the ordering cost decreases and carrying cost increases with increasing order quantity, and their intersection point gives the optimum EOQ value. The reconciliation of steel reinforcement was carried out to compare the total available steel, consumed steel, allowable wastage, actual wastage, and closing stock. The analysis showed that out of 493.81 metric ton of available steel, around 292.89 metric ton was consumed, while the actual wastage was limited to 8.2 metric ton, that is about 2.8%. This is under the allowable wastage limit of 3%. This indicates effective material utilization, proper inventory control, and reduced material loss during execution. Next, the HML analysis were performed based on the unit cost of material. In the high category, binding wires, steel, and AAC blocks were identified because of their higher unit cost. These materials require strict monitoring, secure storage, and careful procurement to avoid wastage and theft. In the medium category, cement and admixtures were included, as they have moderate unit cost and required periodic monitoring and plant procurement. In the low category, sand and coarse aggregates were classified because of their lower unit cost. These materials required comparatively simple inventory control practices. Overall, the HML analysis helps prioritize material, focus, and improve resource allocation based on material cost importance. Finally, the ABC analysis was carried out based on annual consumptions of the material. In category A, steel and cement contributed the highest percentage of total material cost, even though the number of items is limited. Therefore, these materials require strict control, accurate planning, and close monitoring. In category B, AAC blocks, coarse aggregates of 20 mm, and sand aggregate showed moderate cost contribution and therefore required periodic review and optimized procurement planning. In category C, coarse aggregate of 10 mm, admixtures, and binding wires had lower cost impact and can be managed through simple inventory control methods and bulk procurement practices. Overall, both HML and ABC analysis help improve inventory management, cost control, and procurement efficiency by identifying critical materials requiring greater management attention. From the above discussion, proper equipment planning improved productivity, cost control, and workflow efficiency. Hiring the tower crane for 63 months at approximately 49.3 lakhs was more economical than ownership costing around 1.57 crores. Reinforcement equipment achieved a cost efficiency of approximately 7.3 rupees per kg of steel handled. RMC equipment achieved a cost efficiency of approximately 293.62 rupees per cubic meter for handling about 51,740 cubic meters of concrete. In the quality management plan, QAP, NCR, checklist, and inspection ensured systematic quality control during execution. The developer had the highest involvement in maintaining construction quality and execution coordination. Regular inspections and testing helped reduce defects, reworks, and quality issuance. Clearly defined stakeholder responsibilities improved coordination, accountability, and compliance. From the material inventory management, EOQ, ABC, and HML analysis improved inventory control and material utilization. The optimum EOQ for AAC blocks was found to be approximately 377.37 cubic meter, balancing ordering and carrying cost. Reinforcement wastage was controlled within the allowable limits at around 2.8%. Steel and cement contributed the highest share of material cost and therefore require priority monitoring and control. Thank you.